Good morning all. Here are two circuit boards from the Berges ACM-D2A 11.0 kilowatt. This is the display and I/O board, and this is the control board. And they're both mated together by this connector right here and this connector through this ribbon cable. Now, I had always been curious, and I never tried to figure it out until just the other day. These digital inputs, they're either active high or active low. And I thought to myself, how in the world do they do that? So I mapped the circuit out. It's generally in this area right here, and it is fairly complex. I'll bring my schematics over and we'll talk about what's going on. Here's the cover plate for the display and I/O board. This terminal 7, 8, 9, 10, 11, 10 and 11, that's your enable. 7, 8, and 9, that's where you apply your speed reference. 12, 13, 14, 15, 15 and 16. 15 is reverse, and 16 is run forward. And I always use 16 connected to 14 because most times 15 is disabled. It doesn't work. Let's move all this out of the way here. We'll bring the first drawing in. See if you can see that. Now I'm going to be upside down. I believe I'm correct. Let's see. What are we at here? Yes, okay. You're oriented correct. Sometimes I put the paperwork in here so that I can see it. But it's upside down for you, so I'm trying to get it correctly and applied. So let's bring this board back in here. Here is 11, 15, and 16 on this connector right here. TB1, terminal board 1. And like I said before, 11 is enable and 16 is run forward. Now the question that I had in my mind was, how in the world is that programmable? Either I apply a high here or pull this input to ground. So 11 would be connected to 10 and 15 and 16 would be connected to 14. That's all logic ground back there to the control board. How is it that they can set this up so that it's either a high end or a low end? And so I mapped the circuit out, and right here we have a 74HC240B1. That's an octal buffer driver IC. And here we have an SN74HC273. That's an octal D flip-flop. Now, this is the interesting part. The software, the saved parameters set whether this output is active high or active low. And if we look here, we see that the Q outputs are tied back to this pin right here at this point. And this Q output, that would be Q0, Q1 is tied to 15. Q2, that output, is tied to 16. And they have a 4.7 kilo ohm resistor in that circuit. What does that do? Well, let's say we load this output. It's a latch, its data is saved. When we first fire up that drive and it goes and grabs the parameters and starts setting this I/O up. If we put a high, this right here is the ribbon cable going back to the processor. If we put a high here and latch it to the output, that makes this point right here at 5 volts. And we have, in essence, a 4.7 kilo ohm resistor tied to pin 11 pulled up to 5 volts. It's a pull-up resistor. And the same here. If we set a high here and latch it to the output, this is your D inputs and this is your Q outputs. If we put a high here on 14 and then latch it to the output, now terminal 15 has a pull-up resistor of 4.7 kilo ohms pulled up to 5 volts. And the same on terminal 16. We apply a 5 here and clock it to the output, and now 16 has a 4.7 kilo ohm pull-up resistor. And in that case, since this is a pull-up resistor, we have to pull these inputs to ground. They're active low. Pull to ground to activate that input. And when we do that, the input goes through the buffer back out the same pins. So 15, 14, and 13 were to set up the pull-ups, and now 11, 15, and 16 over here on the terminal board go through the buffer to 15, 11 to 15, 15 here to 14, I'm upside down, 16 to 13, and back to the processor. Now, what if we want to have to apply a positive voltage to these inputs? Well, for this instance, we apply 0 volts to D0, clock it through the other side, and we have 0 volts right here, and now we have a 4.7 kilo ohm pull down resistor, and we have to apply positive 5 volts to the input. And same with 14. We apply 0 volts here, clock it to the from D to Q, and now this resistor right here, this 4.7 kilo ohm resistor, is a pull down resistor for TB1 terminal 15. And on 13, we apply 0 volts here, a low, clock it to the other side, and this point right here becomes 0. And now we have 4.7 kilo ohms pull down resistor on terminal 16. So, isn't that fascinating? So the setup goes this way, and the actual switch position on the input goes this way. Isn't that amazing? And that's why sometimes you'll get a Berges in the shop where you could put a switch from terminal 11 to terminal 14 and switch that, but nothing happens. It's because it's set up to be plus 5 volts in. Amazing. Let's go look at the controls of these two ICs right here. The 74HC240 and the 74HC273. Let's bring this over here. Okay, on the 74HC240 B1, when terminal 28 is high, the outputs of that octal buffer driver IC are in tri-state. And when terminal 28, this is the 40-pin ribbon cable going back to the control board, when it is low, then the outputs are active. You can pass from the input to the output. On the SN74HC273N, that is our octal D flip-flop. We have to clock the data from the input, the D side, to the Q, the output side. Now master reset down here, it's pulled up to plus 5 volts. It's always out of reset. The clock comes from terminal 22 through a forward bias diode and a 2.7 kilo ohm resistor to clock that data from the D side to the Q side. Now if the it's a low to high transition to clock that data through that flip-flop. Let's go over here and what do we have here? Here is an MC74HC138AN, and that's a 3-line to 8-line decoder. And you'll see these ICs a lot for addressing, and that's what we're basically doing. We're addressing those ICs. This is on the control board. So 22 and 28. Here's 28, here's 22. That's your clock and your output enables. And Y4, that's on pin 10 of the 74HC138. That also goes to the transmit receive of an SN74HC245. This is on the control board. I think that's everything. Now I didn't flesh this out. I should have, but it's going to run back to the processor to address your clock and output enable for that 74HC240 and the 74HC273. That's all going to go back, be controlled by the addressing of the processor. I might follow that out if I ever have to, but let me show you where all these things are. This IC right here, this is your, we're back on the I/O display board. This IC right here is your 74HC240. Your 74HC273 is right here beside this relay. Here's your resistors that we showed. Let me bring that page back in. There's your 10K resistors and your 4.7K ohm resistors. That's these guys right here. Huh? Isn't that amazing? Look at that. That's how they program these inputs to either active high or active low. That's insane. It's actually pretty genius. Right here is the 74HC138. That's being that sets the clock pulse and the output enable for these two guys. And this IC right here, this is the 74HC245. That's a bidirectional buffer. You have an A side and a B side, and depending on how that TR pin is set, if it's high, then data transfers from the A side to the B side. If it's low that you receive, the data is transferred from the B side to the A side. Okay. I probably missed something, but this would be a fun circuit to try on breadboard to duplicate that action. I'll put these pieces of paper up at the end of the video, and you can experiment with your Berges ACM-D2A 11.0 kilowatt inverter drive, the I/O board, the I/O and display board. Have you a good day, all. We'll see you in the next one.